Hi, I'm Salva. I study computer science at the Technical University of Darmstadt, which is in Germany. Right now, I'm having the pleasure to be at the bottleneck and be mentored by Ben Böcking and Artur Dubowski. Today, I'll be presenting the work that we created during RIS, which falls under the research area of weak supervision. And so a bit of background on that. The broader motivation for weak supervision is that machine learning methods often require large amounts of labeled data. So for instance, the ImageNet dataset has over 14 million of labeled images. And what's currently often done is to hand label, which is of course very costly, and especially when domain experts need to be involved. As such, this represents a major bottleneck for deploying machine learning to new domains. A promising alternative is weak supervision, and more specifically, data programming. In this framework, the user can encode his or her domain knowledge into labeling functions, which may be domain heuristics, knowledge bases, or pre-trained classifiers that label subsets of the data noisily. For instance, the ones on the slide could be heuristics for a sentiment analysis task. These labeling functions often have different types of dependencies. For instance, the one on the slide, we can see the second labeling function likely fixing the vote of the first when both label. That is when the words wouldn't recommend appear in some movie review. And more generally, this happens when the LFs operate on same or similar inputs, or often they are also deliberately defined by the user to reinforce or fix less precise votes of other labeling functions. So in this framework, we model the joint distribution of the labeling functions and the latent true label that we want to estimate as a generative model, more specifically as a factor graph, which is a type of probabilistic graphical model. And we can then estimate probabilistic labels for our unlabeled data that may then be used to train any downstream classifier as a neural network. The name givers for the factor graph, the factors, are simply functions that relate random variables to each other. And we can encode in them different dependency types, such as fixing, priority, or correlatedness. Now, even though there has been extensive work on modeling and learning these dependencies, the value of this additional step of modeling them with respect to downstream performance is not really well understood. In particular, we aim to identify and quantify the impact of simply ignoring dependencies, which is a common approach in popular data programming libraries, as well as related research. And so we explore this gap by characterizing settings in which modeling dependencies boosts performance, as well as those in which it does not, and also quantify the impact that we can expect. Surprisingly, we find that it can also worsen performance by up to 4 AUC points. For our experiments, we first synthetically generate labeling function outputs by kind of reversing the usual procedure of learning the parameter. Instead, we provide these weights and thus have full control and knowledge over the number of dependencies and their strength. Additionally, we do experiments on the IMDb sentiment analysis dataset, where we select a set of labeling functions that label on certain words appearing in a movie review. For instance, the word recommend. And so to have a proxy for the true dependencies in the IMDb dataset, which of course we don't know the true dependencies, we can use the true labels and compute the resulting factor values. Again, the factors are just functions for each data point, which we then sum up over the whole training set. So for instance, for the fixing factor here on the slide, this would mean to sum over all data points where the words wouldn't recommend appears and the true label is indeed negative for that data point. For a given factor, we then choose to model the k dependencies with highest positive total value. And so on this slide, you can see some examples for dependencies. The factor column can be regarded as a dependency type and the factor value as a dependency string. As you can see, they make sense, the dependencies. And we will be coming back to them later. Now, on to our experiments. First, for the synthetic data. So here we start with a set of 4 fairly accurate labeling functions, and then incrementally add correlated but uninformative labeling functions. Uninformative meaning that their accuracy is close to 50%, which is rather bad. And so what we can see here is that if we model their correlation, that is the orange line, we can keep the performance from the good labeling functions. Whereas if we ignore it on the blue line, the performance can drop by up to 6 AUC points here. In this similar experiment, we just lessen the difference in accuracy between the good and bad labeling functions. That is, the bad LFs are only slightly worse, but the correlation of the bad labeling functions is stronger. And we can see that even in this case, where they are more or less have a similar accuracy, it still hurts. A bit less, but it still hurts to not model these dependencies by 3 AUC points here. Coming back to the IMDb dataset, we first plot in this slide the difference with respect to baseline performance of not modeling any dependencies, which is the red line here, which amounts to around 81% AUC, which is fairly good. And so when we observe a marginal boost in performance when modeling the strongest 5 or 15 dependencies, the main takeaway is the following. We surprisingly find that modeling more than just a few dependencies significantly deteriorates downstream performance by up to 4 AUC points as compared to simply ignoring them. Moreover, this performance drop intensifies as we go to the right. That is, as we model more slightly weaker dependencies. Again, the table from before, just to reiterate that these dependencies do seem to make sense. Like for me, bad modeling a reinforcing dependency between bad and absolutely horrible for the negative sentiment seems to make sense. Now, to a final experiment where we repeatedly subsampled 10 to 70 labeling functions out of the set from before, 135. Well, what we observe is that often the impact of modeling dependencies is marginal, while for other subsets it does boost performance, here in particular, and for again others it worsens performance. Over here. Also, what we can observe here is that the cases where it does help the most are mostly on the left side. That is where the baseline performance of not modeling dependencies isn't too good. Here. As well as when we have rather few labeling functions, like 20, because for 70 we hardly see any boost in performance anymore. But instead do see the worsening, which doesn't happen for 20, almost. All in all, we can say that when the signals from the LFs alone is already pretty strong for estimating the true label, the addition of modeling dependencies doesn't help too much, or can even worsen performance. To conclude, we have demonstrated various possible impacts of modeling dependencies, in particular, that it can significantly worsen downstream performance. As such, ignoring dependencies is a reasonable baseline, since the boosts that we could expect from modeling them aren't like super large, as seen, and it can in fact also lead to a worse performance. This may come surprisingly and emphasizes the importance of our presented work to gain a better understanding of it. Thanks for watching.